Today we're going to be talking about measuring. And I know that seems like something that we shouldn't have to talk about, but there are actually some important details and techniques that we need to use to be able to measure accurately and well in chemistry. So our job today is a few things. One, we're going to distinguish between measuring something and counting something, which seems very similar but is different. We're going to actually look at fundamental versus derived units, and we're going to give some examples of those. And we're going to talk about how measurement technique affects what we're doing. We're going to talk about how we find the doubtful digit of a measurement and why measurement standards are so important. So first things first, what's the difference between counting something versus measuring something? So counting something is going to involve only whole numbers, only the integer numbers, because fundamentally counting ignores everything about something other than whether it exists or not. If I am counting the ducks at my farm, I don't care whether it's a big duck or a small duck. A big duck is one duck. A small duck is one duck. A brown duck is one duck. A mallard duck is one duck. That's all I care about. Is it there or not? So there are a lot of things that we count all the time. You could count days until the end of the quarter, or pages in a textbook, or minutes until the bell rings. You could count the number of students in a class. But counting numbers are always exact. You can't estimate that you have a third of a duck, because then you don't have a duck anymore. You have a problem. It's either a duck or it isn't. It's either a student in a desk or it's not. Measuring, on the other hand, is fundamentally different. Measuring is so important because it's one of the biggest things we do in science. It's really the basis of all of our scientific laws. And measuring is going to involve the whole set of real numbers. That means we'll have whole units and parts of units. And how accurately we can state something depends on how much we know about it. So let's start with a broad example. Let's say I ask a student how old they are, and they say that they're 16 years old. Well, unless it is that student's exact birthday that day, then that is a rounded off answer. That's not exactly how old they are. So if you say, well, is that really exactly how old you are? You might say, well, I'm 15 years and 8 months old. But if you actually got more information, like say you pulled out your birth certificate, you could get an even more exact answer. You could say 15 years, 8 months, 29 days, and 7 hours. I like to give this example because it's fun. My husband and I have the exact same birthday, but we're not the same age. He's older than me. So once we had been dating for a while, we actually did decide to pull out our birth certificates and figure out exactly how far apart we were in age, even though we had the same birthday. Yes, we're both enormous nerds. I know. But it turned out we were 4 years, 6 hours, and 11 minutes apart. And we couldn't get any more accurate than that because birth certificates don't include information on what second you were born. So that was as far as we could get. Now, when we are doing a measurement, we are almost always going to do this as a decimal number. And there is actually a reason for that. And if you use a exact fraction, that is implying that you know that number out into infinity. It is precisely, perfectly, exactly, say, 1/2 of an inch or a centimeter. And the problem is we very rarely know something exactly, perfectly on forever. Because at some point, I'm going to not really be able to see a difference between the marks on my ruler. They're going to be so tiny I can't really see between them. So instead, we put things in decimal numbers. so that we are indicating how well we can measure that number. So measurements are, as a definition, accurate descriptions of the quantitative or numerical properties of an object. And why we need to care so much about measuring is because almost every experiment in science involves measuring changes. If we change one variable, what happens to something else to see if they're related or depend on each other? So for example, we could do a reaction and say, how much does the mass change when I do this reaction? Or you could push something and say, how much did the position change when I put this amount of force on it? And if we don't measure well, if we don't use precise and accurate measurements, then we could actually not really be able to determine a relationship between those variables. If I want to find out the change in mass when a reaction happens, I'm not just going to hold two beakers in my hand and say, well, no, maybe this one feels a little lighter, or maybe this one doesn't feel like it changed at all, because my hands are not very good measuring equipment for masses. I would use a balance to do that, something that can read this much more accurately and precisely. Fundamentally, measurements have two parts, and they always need to have those two parts. They are numbers, decimal numbers, and units. It's really important that all of your measurements include some units. We don't have any scandalous naked numbers in chemistry class because it matters. If I'm going to measure something, it absolutely matters whether I'm measuring 14 centimeters or if I'm measuring 14 meters or 14 kilometers. If I measure 14 centimeters, that's an object that I could easily hold in my hands. 14 centimeters is just this much of a ruler. 14 kilometers is more than a 10K race. So I just can't say 14. It really matters what my unit is to give someone a sense of scale. Remember, it's important that we communicate our science to other people. The other thing that we need to do when we're communicating about a measurement is we need to think about all using the same measurements, using a standard measurement. If we're all going to work together, we have to agree on how we measure. So imagine if you're all going to build a house. If you're going to all build a house and you're going to measure out using your own foot as 1 foot, we're going back to medieval times. Well, my foot is a different size than Mr. Mora's foot. So if Mr. Mora paced out one side of the house using his feet, and I paced out the other wall of the house using my feet, there's very little chance that we're actually going to end up meeting. And so there's really no way that we would be able to follow the plans for our house. And if the people framing our walls in wood are using inches and the person ordering the carpet is using meters, then they're going to order a carpet that is way too small to fit and fill up my room. We need to all know what we're talking about together. There's a famous story about a Mars probe, of billions of dollars of Mars probe, of years and years of science and design and travel, and it crashed into the surface of Mars. When the scientists went back and did the error analysis, oh my gosh, what went wrong? We just crashed billions of dollars of work and time into the surface of Mars. They found one group of engineers was using meters and the other group of engineers was using miles. And that difference was enough to cause a catastrophic mistake. So when we are working in science, we are going to be using the metric system, And we're going to be finding some fundamental units that we can all agree on. Most of the things that we measure in chemistry class are going to depend on 3 of the fundamental units, or we're going to be able to find them using those 3 fundamental units: length, mass, and time. There are other fundamental units. I have them on a slide in a minute, but a lot of the things that we measure have to do with these 3. So if I know the length of something, if you think about it, I can find a lot of other things about that. If I know the length of 2 sides of something, I can find its area. If I know the length of all 3 sides, the length, width, height, then I can find its volume. And there are other things that you almost don't even think about involving length, like speed. How does speed involve length? Well, think about a speed limit sign. It's 40 miles per hour. That's a unit of length. Miles are a unit of length. Density is a mass over a volume, and volume is derived from length. There are a lot of things we get from mass as well. Like I mentioned, density is something like grams over cubic centimeter. So grams is our SI unit of mass, a kilogram, and mass is also used in calculating force, in calculating power, in calculating energy. Lots of things involve mass. And also, if I go back to things like my speed limit, it was miles per hour. So we had a unit of length there in miles, but we also had a unit of time. And we find time in a lot of other measurements as well. So using these 3 fundamental units, we'll get almost everything that we measure in chemistry class. So in the SI unit, our fundamental units have a given metric system unit. The SI unit for length is the meter. And over the last time, and in fact, even just a few years ago, we actually finally got all of these fundamental units away from being defined by some physical object and into being defined by fundamental constants of the universe. So the SI meter, there's not like a meter stick somewhere that is the official meter. The SI meter is actually defined by the speed of light. And light always travels the same speed as long as it's moving through a vacuum. Doesn't matter where you are in the universe. The SI unit for mass is the kilogram. We very rarely do things on kilogram scale in chemistry class. Most of the time we're using grams or milligrams. And actually mass now is defined by a certain amount of energy, because you can see the M in E equals mc squared. C is in fact the speed of light, one of those fundamental physical constants. And time, the SI unit, is the second. So if you've ever heard of an atomic clock, this is how we define the SI second. It actually has to do with the transition or the movement of electrons in atoms of the element cesium. So it really is measuring something in an atom. That's why it's an atomic clock. Here are my other SI-based units. We're actually going to use 5 out of these 7 base units in chemistry class. We talked about time, length, and mass. But during the course of this year, we'll also use Kelvin temperature, the absolute temperature, and we will use the amount as the mole, a ton. In AP chemistry, we'll actually work in that 6th base unit. We will talk about using electric current, like a battery, and that electric current is the ampere. I don't think in chemistry we're going to use luminous intensity. That's more something that you will use in physics, but it is one of those 7 base units that other things are derived from.